Welcome back. I hope that by exploring the applet, you all agreed on how to restrict these. Namely that for sine, you agreed we should take a number, an angle between minus pi over 2 and positive pi over 2. That seems the most natural in this graph, right? You're going right around the origin, and when you go from minus pi over 2 to pi over 2, there are no repeated y values, but you get all of the y values from minus 1 to 1. If you did something smaller like 0 to pi over 2 and someone asked you what's the inverse sine of negative 1, you wouldn't have an answer. Similarly for cosine, the most natural one that the whole planet has agreed on is to go from 0 to pi. And for tangent, the same as for sine, minus pi over 2, pi over 2. You might be thinking that these inverse trigonometric functions don't have any use, but in fact, if you want to decide where the best place to sit in a movie theater is to optimize your viewing pleasure, you need to be able to understand inverse trig functions. So let's practice with them a little bit more. Arcsine of 0. So by our definition, arcsine of 0 is the angle between 0 and pi. I'm not going to write that, but the angle whose cosine is 0. So you could look at your graph of cosine from before and see where the cosine becomes 0, and you will discover that that happens at pi over 2. It happens, did you get that on camera? It happens at other places as well, but we've agreed that we're always going to choose an answer between 0 and pi for our inverse cosine function. Arctangent of 1 is the angle, and again, between minus pi over 2 and pi over 2, whose tangent is 1. So as we define tangent, it's sine over cosine. So you've got to find a place where sine and cosine are equal, because the fraction's only going to equal 1 if the top and the bottom are the same. So you have to ask, where are sine and cosine equal? And that is at a 45-degree angle, except we've decided we're not going to use degrees. We're going to use radians, and 45 degrees is the same as, that's a 2 by the way, is the same as pi over 4 radians. Now how about this one? I'm asking you to give me a number for arctan x plus arctan of 1 over x, even though I haven't told you what x is. All I've told you is that x is positive. Meaning this must work whether x is 1 or 2 or pi or 27 or 1/27. They must all work. So let's figure out how this happens. So arctan of x is an angle. So let's give it an angle name, like theta. So suppose theta is arctan of x. I can already hear you. You don't want to work with inverse trig functions. So how do we get rid of the inverse trig function? We need to apply the inverse of the inverse trig function to each side. So how do I get rid of an arctangent? I apply tangent to each side. So therefore, tangent of theta is the tangent of the arctangent of x, but the tangent of the arctangent of x will just be x. So I want to make an angle whose tangent equals x. Let's see if I can draw such an angle. I'm going to draw a right triangle. Here's my theta. We want the tangent of this angle to be x. Tangent on a triangle is opposite over adjacent. So somehow I want opposite over adjacent to work out to be x. Now there's infinitely many ways you could choose to put these. You could put 11x here and 11 here. You could put 35x here and 35 here. But and they'll all work, that's fine. But the easiest way, I think, would be to put an x here and a 1 here. So can we agree that we have now created an angle, theta, that equals arctangent of x? This angle is arctangent of x because the tangent of this angle is x. Now we want arctangent of x plus arctangent of 1 over x. So this angle theta equals arctangent of x. And because of the way the problem is constructed, can you see another angle in this triangle that equals arctangent of 1 over x? Meaning an angle whose tangent is 1 over x. What about this one? what's the tangent of this angle? Tangent is opposite over adjacent, so 1 over x. So this angle equals the arctangent of 1 over x. And this is true no matter what x is. The tangent of this angle is x over 1. So this angle is arctan x. The tangent of this angle is 1 over x. So this angle is arctangent of 1 over x. You can go back and reread this definition of arctangent, if that helps. But what have we got here? We want to add together these two angles, arctan x plus arctan 1 over x. This angle plus this angle, the whole thing is a triangle. This is a right angle, meaning if we're doing it in degrees, this is 90 degrees. So no matter what this is, I know that this one plus this one must add up to the rest of the triangle, and a full triangle should be 180 degrees, or pi radians. So if I've already used 90 degrees here, these two must add up to 90 degrees as well. Or in radians, what is 90 degrees? It is pi over 2. So you can confirm this on your calculator by plugging in different values for x. And you will see that as long as x is positive, when you take arctan x plus arctan of 1 over x, you'll always get, your calculator will say 1.57 something, always get pi over 2. Or you could graph this function, and what should the graph of it look like? If it's always equal to pi over 2, whenever x is positive, it should just be a horizontal line at around 1.57. All right, so that's sort of just interesting on its own, but it was also meant to help us with the very last inverse trig problem that we're now about to do. Several weeks from now, when we're doing calculus on inverse trig functions, we'll end up with lots of expressions like this, where you have an inverse trig function inside of a different trig function. If they were the same, they would cancel each other out. We'd just get x. Everything would be great. But they're never going to be the same. So we're going to try at that point, well, we're not going to try, we're going to succeed at that point in rewriting all of those without using any trigonometric or inverse trigonometric functions. There's always a way to simplify these so that you don't have any trig or inverse trig functions. We're going to do something similar to what we did there. We're going to start with this arc cosine of x. And let's remember what arc cosine of x is. It's an angle. So I'm going to call it theta. Theta is the angle between 0 and pi whose cosine is x. Just as we did there, we're going to say we'd rather not work with inverse trig functions if we can avoid it. So how can I get rid of this? I need to apply the cosine to each side. So cosine of theta is the cosine of the arc cosine. They cancel each other out because they're inverses, equals x. Let's see if we can draw such an angle on a triangle. So if I make this angle theta down here again, it doesn't matter which one you pick. Just, of course, don't pick the right angle. You could pick this one or this one. I want the cosine of this angle to be x. Cosine on a triangle is what over what? It is adjacent over hypotenuse. So I want adjacent over hypotenuse to equal x. The easiest way to make that happen would be to call this x and this one. So now we have created an angle whose cosine is x, meaning this angle is arc cosine of x. What do we ultimately want? We want tangent of arc cosine of x. I've decided to rename arc cosine theta, remember, so I'm just trying to figure out what tangent of theta is. And as we just discussed up there, tangent of theta is opposite over adjacent. So the opposite side, I don't know what it is. I'm going to call it y. The adjacent side is x. So this is y over x. But my original expression didn't have any y's in it, right? It just had the letter x. Therefore, my answer should not have any y's in it either. It should also just have x's in it. So can we figure out what this y is in terms of x? And I hope you're saying yes, because if there's only one theorem to know, it's the Pythagorean theorem. So the Pythagorean theorem, Pythagorean, we should spell it right, theorem, says what? That if I square the hypotenuse, it's the same as the sum of the squares of the two legs. And in particular, the one that I don't know here is y. So if I solve, 1 squared is just 1 minus x squared equals y squared. Here we're talking about a length on a triangle, so I can't have a negative, so I don't need to worry about putting a plus or minus over here. Square root of 1 minus x squared. Meaning that now I can replace this as square root of 1 minus x squared all over x. That makes sense? You had one trig function inside, an inverse trig inside of a trig function. You assigned an angle name to the inverse trig function, got rid of the inverse trig function by applying its inverse, drew a triangle, labeling, putting the x and the 1 where you wanted them. And then we didn't know what the third side was, but the Pythagorean theorem came to the rescue. Pythagorean theorem, by the way, was not discovered by Pythagoras, known way before Pythagoras, but just got named after him. And here we have rewritten this completely without any trig or inverse trig functions. In other words, if you put into your calculator this graph and this graph, they would be exactly the same. You'll get a chance to practice this on the homework, and then we will do this again. We will see where it's really useful in about week 6 when we are doing derivatives of inverse trig functions. But for now, we have a check your understanding for you.